Ready to make a real impact every day? Join the Active Day Home Care team and help clients maintain their independence in the comfort of their own homes. Make a difference in someone's life as you provide essential daily assistance and protect their health and happiness. Earn up to $20 an hour and enjoy additional perks like optional daily pay, 401k, paid time off, ongoing educational training, and more. Join a team that values care, compassion, and your professional growth. Visit activeday.com to apply.
Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. This week in astronomy, Vera Rubin First Images, the hunt for Planet 9 and universe's first stars. Vera Rubin Observatory captures dazzling debut images. After more than 20 years of planning and construction, the Vera Rubin Observatory in Chile has finally revealed its first images, marking a milestone in modern astronomy. Situated atop Cerro Pachón in central Chile, the observatory benefits from exceptionally clear, dry skies that are perfect for deep space observation. This massive U.S.-funded project is equipped with an 8.4-meter telescope and the most advanced digital camera ever built, and it promises to reshape how we observe and understand the universe. One of the newly released images is a stunning composite of 678 exposures taken over a span of just 7 hours, capturing the Trifid Nebula and the Lagoon Nebula, both star-forming regions located thousands of light-years away from Earth. These nebulae appear in brilliant pinks and reds, revealing intricate structures and details that were previously too faint or invisible to detect. These nebulae, located within the Milky Way, are stellar nurseries where new stars are born, and the Rubin Observatory has presented them with unprecedented clarity. Another of the observatory's inaugural images presents an expansive view of the Virgo cluster, a massive collection of galaxies. Even a small portion of the image is rich with detail, showing bright stars in the foreground and countless galaxies in the background, each a vast island of stars millions of light-years away. Alongside the images, the Rubin team also released a remarkable video called The Cosmic Treasure Chest, which begins with a close-up of 2 galaxies and then zooms out to reveal about 10 million more, emphasizing the incredible scope and depth of the universe the observatory is now capable of capturing. The observatory is supported by powerful data processing systems that will enable it to carry out its flagship initiative, the Legacy Survey of Space and Time, LSST, beginning later this year. This project will systematically scan the night sky every night for 10 years, detecting even the faintest changes with a level of precision previously unattainable. These observations are expected to revolutionize our understanding of the universe by mapping billions of galaxies, tracking cosmic phenomena, and uncovering new celestial objects. The observatory is named in honor of Vera C. Rubin, a trailblazing American astronomer whose groundbreaking research offered the first convincing evidence of dark matter, the elusive form of matter that does not emit light yet exerts gravitational forces throughout the cosmos. Her work fundamentally changed the field of astrophysics. Alongside dark matter, scientists also study dark energy, a mysterious force believed to be driving the accelerating expansion of the universe. Together, dark matter and dark energy are thought to constitute approximately 95% of the entire universe, yet their true nature remains one of science's greatest mysteries. The observatory is a collaborative effort led by the U.S. National Science Foundation and the Department of Energy, and it has already proven to be an extraordinary tool in other areas of space science. In just 10 hours of observation, the Rubin Observatory detected 2,104 previously unknown asteroids within our solar system, including 7 near-Earth objects that have been confirmed to pose no danger. For context, all other ground and space-based observatories together typically discover about 20,000 new asteroids annually, highlighting Rubin's unmatched capabilities. It is also expected to become the most efficient facility for detecting interstellar objects, rare visitors from beyond our solar system, offering new opportunities to study these mysterious travelers. More images from the observatory were scheduled to be released later the same day, and excitement continues to grow around what this new facility will reveal. With its cutting-edge technology, powerful survey capacity, and mission to answer fundamental questions about the cosmos, the Vera Rubin Observatory stands as one of humanity's most ambitious astronomical undertakings, poised to unlock secrets of the universe and inspire future generations of scientists and dreamers alike. New clues emerge in the hunt for Planet 9. For many years, astronomers have been intrigued by a strange puzzle unfolding in the distant reaches of our solar system. Far beyond Neptune lies a region filled with icy, rocky remnants known as Kuiper Belt objects. These small celestial bodies don't drift randomly as one might expect, but instead appear to be clustered in oddly aligned orbits, behaving as though they are being guided by something massive and unseen. The leading theory to explain this curious arrangement proposes the existence of an enormous hidden planet, unofficially named Planet 9, gravitationally herding these distant objects into their mysterious paths. According to current models, if Planet 9 exists, it would be a true colossus, anywhere from 5 to 10 times the mass of Earth, and orbiting the Sun at a staggering distance of 400 to 800 times farther than Earth does. At that remote location, it would be far too faint to detect with ordinary telescopes that depend on catching the light the planet reflects from the Sun. Reflected sunlight weakens dramatically with distance, making this approach nearly hopeless for such a remote target. This is where a group of scientists led by Amos Chen from National Tsinghua University introduced a groundbreaking shift in strategy. Instead of relying on visible light, which fades drastically with distance, they turned their attention to thermal radiation, the faint heat that all objects emit. The physics here gives them an edge. While reflected light becomes 16 times dimmer every time you double the distance from the Sun, heat emissions only drop by a factor of 4, offering a more favorable path for detection. To pursue this line of investigation, the team used data from the AKARI space telescope, a Japanese satellite that performed one of the most sensitive all-sky surveys ever in far-infrared light, the perfect region of the electromagnetic spectrum to detect the faint thermal glow of a cold, distant world like Planet 9. Unlike telescopes on Earth that struggle with interference from the planet's own atmosphere, AKARI's view from space allowed it to pick up extremely subtle signals, precisely the kind Planet 9 would give off. The team focused their efforts on a specific swath of sky. This area wasn't chosen at random, but based on detailed computer simulations that predicted the most likely location for Planet 9, inferred from the unusual orbital paths of the Kuiper Belt objects. The challenge was immense. In a sky teeming with stars, galaxies, cosmic dust, and the occasional stray asteroid, how does one pick out a single slow-moving planet? The answer lay in motion. Planet 9 wouldn't zip across the sky like a comet, it would appear stationary over the course of a single night. But if observed across weeks or months, its position would subtly shift against the background stars. By comparing infrared images from AKARI taken at different times, the researchers looked for objects with just this kind of movement. To avoid being misled by false positives, they carefully filtered out known sources of noise, such as passing cosmic rays and distant galaxies that don't move. After this painstaking process, they identified 2 promising candidates. Both objects were located in the predicted region and emitted infrared light consistent with what would be expected from a massive, distant planet. This does not yet prove the existence of Planet 9, but it marks the most compelling lead uncovered so far. These potential detections were detailed in a paper published in the Publications of the Astronomical Society of Australia. The work is far from finished, however. These objects now require follow-up observations with more powerful instruments to confirm whether they behave as a true planet should, slowly shifting across the sky in a way that matches predicted orbital paths. There is also the possibility that they could be something else entirely, such as background galaxies or other infrared-emitting bodies masquerading as planets. Still, the significance of this step cannot be overstated. If either candidate turns out to be Planet 9, it would fundamentally reshape our understanding of the solar system's architecture and history, offering fresh insights into how planetary systems form and evolve. Just as importantly, this search showcases the value of creative thinking in science. Sometimes, the key to finding a lost planet isn't seeing it directly in the sunlight, but rather sensing its quiet warmth radiating across the cold vastness of space. Radio signals reveal clues about the universe's first stars. Understanding how the universe changed from being completely dark to being filled with light is one of the biggest questions in astronomy. This moment in time, when the very first stars and galaxies began to form, is called the cosmic dawn. It marks the beginning of everything we now know: galaxies, planets, and eventually life. But even with our most powerful telescopes, we can't see these very first stars directly because they are too far away and too old. So scientists have had to find new and creative ways to figure out what those stars were like. One of the most promising methods doesn't involve light at all, but rather a special type of radio signal. This signal is created by hydrogen, the most basic and abundant element in the early universe, and it can tell us a lot about what was happening over 13 billion years ago, just 100 million years after the Big Bang. A group of astronomers, led by the University of Cambridge, has developed a way to study this hydrogen signal, known as the 21 centimeter signal, to learn about the masses of the universe's first stars. When the first stars were born, they gave off ultraviolet and X-ray radiation that changed the behavior of hydrogen atoms floating in space. These changes affected the 21 centimeter signal in very specific ways. By analyzing how the signal was influenced, the scientists believe they can figure out how big those first stars were, how much light and energy they gave off, and how they helped shape the early universe into the more complex one we see today. The team's results were published in the journal Nature Astronomy, and they offer an exciting glimpse into a time we've never been able to study in such detail. One of the key researchers on this project, Professor Anastasia Fialkov from Cambridge, explained that this is a unique chance to understand how light first appeared in a universe that had been cold and dark. This moment, the birth of the first stars, was a turning point, and studying it helps explain how the universe evolved. Fialkov leads the theory team behind a project called REACH, which stands for the Radio Experiment for the Analysis of Cosmic Hydrogen. REACH is a radio telescope designed to detect the faint 21 centimeter signal, and it's one of two major projects helping astronomers unlock the secrets of the early universe. The other is the Square Kilometer Array, or SKA, which is a massive network of radio antennas being built to scan the sky in fine detail. While REACH is still being fine-tuned, its goal is to collect data from the radio waves sent out by hydrogen atoms during the cosmic dawn and the later phase called the epoch of reionization, when the first stars gave off so much radiation that they reionized hydrogen atoms across the universe. SKA, on the other hand, will be able to measure tiny differences in the signal across large areas of the sky, providing a much bigger picture of what was happening during those early times. Fialkov and her collaborators created detailed models to predict how the 21 centimeter signal would behave if the first stars had different masses. Their simulations took into account things like the original mix of elements from the Big Bang, and the effects of X-ray binary systems, pairs of stars where one is a collapsed object like a black hole or neutron star. These systems produce strong X-ray radiation and seem to be more common among the universe's first stars, which are known as population 3 stars. The researchers found that many earlier studies had not fully considered how these X-ray binaries could change the 21 centimeter signal. By including them, they showed that the signal is more sensitive to the masses and brightness of the first stars than previously thought. Radio astronomy is very different from looking at pictures taken by space telescopes like James Webb. Instead of showing detailed images of individual stars, radio telescopes collect patterns and signals from large groups of stars and galaxies. It's like listening to a faint hum and trying to figure out what kind of orchestra is playing, even if you can't see the instruments. But with the right tools and careful analysis, scientists can learn an incredible amount from these quiet signals. The work from the Cambridge-led team suggests that radio telescopes like REACH and SKA will be able to tell us not just that the first stars existed, but also how big they were and how they lived and died. This kind of knowledge could change the way we understand the entire history of the universe. The researchers say these predictions are a crucial guide for the observations now being made from places like the Karoo in South Africa, where the REACH telescope is located. If everything goes as planned, these new tools will soon give us a clearer picture of the first lights in the universe, and finally help us understand how the darkness turned into light.